Welcome to the Shaper Electronics Lab. I'm Jeremy.
I'm Richie.
And we're here to talk a little bit about Origin and how it works. Cool. So let's start with a refresher on how you actually use it in practice. What the tape is, how the camera works. Let's start there, and then we can open it up and see what's on the inside here. A common misconception of how Origin works is how it interacts with the tape to figure out where it is in space and to align designs to your workpiece. So this is Shaper tape. This is our fiducial marking system. And when we say fiducial markers, that's just a fancy word for indicators that can be tracked by a vision system. So Origin has a vision system in it, camera on the back, and you put these markers on whatever it is you're going to cut, and then this camera on the back takes a look at the tape, and Origin figures out its position in space like that. It's kind of like a GPS system. Think of the markers on the tape like GPS satellites, and the camera like the GPS receiver in your phone, figuring out its location based on where it sees the tape. Okay, so I'll move it around, and you can explain what I'm doing here.
I think this is a great opportunity. I've been dying to try this out. We've got a little demo here. This is what the field of view is on Origin, what Origin's camera can see. So you can see we just back this up onto the base of Origin here, and in theory, we should see...
it lines up perfectly. So at any given time, as long as you can see something in this space, Origin can cut. We need to see just a few markers at a given time to calibrate out any error in the system and compute the position of the camera, figure out where Origin is, and then from that we can decide where we're driving the bit to. And so at any given time here, what we actually see on the screen is an augmented view, as if there was a camera mounted in the cutting bit.
Okay, here that is again in non-nerd speak. So basically, Origin takes a picture of your workpiece, including the Shaper tape. And this is a bunch of images that get stitched together to form one large image. The next step is to insert a bit and probe your workpiece. You can probe the workpiece in 3 locations, and doing so creates an XY coordinate system. Now, this might sound complicated, but what's really happening here is Origin is now able to not only track its position in space, but its position relative to an edge of your workpiece. So now you can import your design and set that design at a specific location, like a ½ an inch from one edge or the other. And then the next step is to begin cutting. So while cutting, you steer Origin following the design on screen, and it makes small adjustments to ensure that you stay exactly on the line. Now, it makes those small adjustments because it knows where you're intending to cut and where the tool is in 3D space. Back over to you, Jeremy and Richie.
Okay, so in order for Origin to do all the amazing things that it can do, to see your workpiece in real time, to figure out where it is, to autocorrect your cutting, there's kind of an anatomy of this tool to understand. So up front, we have the business end. This is the spindle motor manufactured by Festool. That's mounted on a Z-axis that allows it to plunge up and down. And that entire Z-axis mechanism is mounted on an XY system that we've created, and we'll show you what that looks like in a little bit. That allows it to move around in an XY area, and that's what enables us to get the correction capabilities of Origin. That's then mounted onto the base plate here with our handles, dust extraction, and then underneath is our skid pad, which is what Origin slides around on and what protects the mechanism that allows it to move around in 3D space. So if we spin it around here.
Now we get to take a look at the party end of Origin. And so Jeremy already pointed out, we've got the display in here that helps us see what's going on back here. Try to do this without blinding everyone, but beside the camera, we have the LEDs here with the diffusers, and then this is the actual camera sensor in the center here that's doing all of the viewing, vision, sensing for our computer vision.
Okay, so we've talked about the anatomy of Origin, and we've shown how it scans workpieces, but that's just kind of like the user-facing side of how this works. Let's get into the nitty-gritty of the actual science and engineering of how we've built this and made it robust and reliable. So first things first, Origin is powered off of wall power, so for safety, let's unplug it, please. So I will go ahead and take those off.
And I'll just hold Origin down to make sure it doesn't fly away.
So I'm just going to pry this off here using an amount of force that feels inappropriate, but actually is fine because we did a really good job designing the plastics for the rear cover. Oh, look at that teamwork. So in the back of the Origin cover, what you'll see is a two-shot plastic rear cover with a rubber gasket and a internal plastic cover that helps keep everything protected from dust on the inside.
Can you walk us through what's this big chunkin' thing down here?
Yeah, so the big first thing you'll notice is our AC/DC power supply. So general architecture of how the power works here is power comes in from the wall and it goes two places. It goes to our AC/DC. That generates the DC voltage that's used by all the compute electronics inside of here and powers our stepper motors for our correction motion. And then the AC power also goes out to our spindle motor, our brushed SM1 spindle motor that's manufactured by Festool. So this guy here is basically making all the power for the compute and the correction motions inside of the tool. That's mounted on a power board that has a bunch of other sensing electronics, helps monitor how the spindle is running. That's how we know if the spindle is on or off when you go to plunge into your material, for example. Generates a bunch of other voltages that are used for the rest of the logic in the system. Moving up, we'll find our main logic board. That's this guy here. Our main logic board has things like motor drivers for our stepper motors, sensing elements, inertial measurement unit. That's how we detect if you're doing a touch-off. And then mounting for our system on module, SOM for short. Our system on module is called the Blade 1. We designed this ourselves, and it's specifically optimized for the use case of robotic power tools. Quad-core processor, similar to what you would find in your phone. Onboard memory, wireless, Wi-Fi and Bluetooth connectivity, and all the other smarts that are necessary in order to capture images from the camera, look at them, run our algorithms that look at those images, figure out where the dominoes are. This is all a computer vision algorithm that runs on our system on chip, which is mounted on the Blade 1 module. We look at that data from those camera images, compute our position in space from that, and then use that to drive back out to the motors. Moving on. So you'll also see a bunch of wires in here. What does the main compute connect to? This goes to our stepper motors, our left and right correction. We'll look at how that works in a second. Our encoders that measure the position of those motors many thousands of times per second. And then flex cables that go up to our display and our camera. So the camera in here takes a picture every 10 milliseconds, and every time that camera image comes through, it goes into our processor here, we analyze it, we figure out our position in space, and then drive the motors to correct for that position in space in real time. So we see the dominoes, image is captured by the camera, image comes from the camera, goes into our processor here, processor figures out where the camera is in 3D space based on seeing this, then computes where the spindle is in space based on its understanding of the tool's geometry, figures out where you want to be on a cut tool path, and then drives the motors in real time to get you onto that path exactly as fast as possible. Sweet.
Awesome.
Okay. What we're looking at back here is our compute. But a big part of what Rishi worked on here is the human-machine interface and the system for driving the z-axis. So let's jump over to those. The human-machine interface, or HMI, that's just fancy word for touchscreen.
Thank you for that segue. We have a couple of handy-dandy props standing by. This is the camera module. Come back to that. And I'm going to reach over here into our test setup, and we'll find also the display module. So start with the display. This is the display module that actually sits in Gen 2 version of Origin. And this is a semi-custom module that we designed and specified ourselves. This is a 720p HD display, capacitive touchscreen, just like you'll find on most devices on your phone or even a lot of laptops these days. And if you were to open your phone or your laptop, you would also find, coming off of the display, is you're going to have one of these flex tails. This is all of the information, all the communication pathway that we have to the display from the compute module that Jeremy was telling us about.
So why this fancy tail? What'd you call it? A flex?
Flex tail, yeah.
Okay.
That's a great question. Flex tail, flexible printed circuit. When you start working on things like HD devices, these need to run so fast and process so much data so quickly that you actually need to make sure that the wires, the circuits, the copper that is on the flex itself has very specific electrical properties in order to make sure that your signal comes through and that you're able to process all of that data. So this is pretty standard for any modern device. And another thing that Jeremy is also referring to is this is kind of a special shape here that we designed to help make sure that at the factory, when they're assembling and manufacturing the units, this has very good retention under vibration because Origin sees a lot of that. And then also that it assembles nice and well without needing to futz with connectors, bending something, or having to route additional wires.
So it's maybe easy to miss that, looking at the back of this, we talked about how it functions for the end customer use of making awesome cuts and interacting with Origin, but every decision in the back here is also strongly influenced by our ability to manufacture it quickly and effectively and to ensure that every unit that runs off the production line is working and is meeting our very high quality standard. So if we look in the back here, we can see the flex that you just mentioned that goes up to the display. Now I see another flex right next to it in a similar size connector. It looks like that's maybe this guy. So what's this?
Yeah, so excellent segue. You'll notice very similar flex design. I'm proud of these flexes. This is the camera module. So this is another module, again, designed by us custom. And you can see that this one has this flex tail coming off of it. It's got some weird yellow greenish rigid part on the back, but then it's got this really cool mechanically designed bracket here. If you look at the back of Origin, this is where you can see we've got the LEDs on either side, and then we've got the camera sticking through this piece of cover glass. So you can imagine if you were to pop this display out, what you'd see staring back at you is something like this, where the camera module is very rigidly installed in there. Again, Origin sees a lot of vibration when it's going through heavy cuts, so we need to make sure that we mount this as strongly as possible. Now, Jeremy grabbed another nice prop here, which is if you unscrew these two screws, what you'll be left with is our vision board. This is our custom camera module we've designed. Again, it's got a flex tail. This is a lot of high-speed HD data coming through. This is an HD camera. We've got some simple onboard electronics for powering everything and making sure that we're going to get very high-quality, low-noise images off of this board. And then we've got some onboard LEDs for workpiece illumination. This is what helps really see the tape, see your workpiece as you're moving Origin around, scanning it in, and trying to work with it. So that's all done on board here, but the real magic is this giant lens sitting in front of the sensor here. Now I wish that we had a microscope and a lot more time to go into the actual construction behind here, but we spent a lot of time and energy designing this module, and in particular this lens, because fun fact, our computer vision application is so sensitive here that even as the plastic and the glass inside this lens heats up, it changes shape ever so slightly, it changes optical properties, and we detect that with our computer vision algorithm. This is the vision system for Origin. So pictures come in through the camera sensor, come over this flex, plug into our electronics, and then we relay that information back over this flex to your HD display so that you can actually see what's going on.
So let's move our human-machine interface, our vision system, off to the side here.
And we'll bring in some of the motor system.
So, okay. Once Origin knows where it is in 3D space, we have to do something with that information. We need to move the motors to get Origin to your cut line as quickly as possible so you get a perfect machine quality cut. Now, there's two parts to that. There's the left, right, or XY correction. That's your correction in the plane of your workpiece. And there's your Z-axis. And so your Z-axis is used to plunge up and down and make sure you're cutting at exactly the right height. So let's talk about the Z-axis first. This is on a lead screw here that moves it up and down. Lead screw is all it is a special screw connected to a stepper motor. So the way this works is there's a stepper motor up here. This is another board designed by Richie that drives the stepper motor, and we send commands to that board. Stepper motor moves up and down, and that moves the carriage up and down that holds the spindle motor. And so when we do a touch off, for example, the way that works is, we mentioned earlier, there's an inertial measurement unit in here. This is the same thing that's in your phone. You know how when you open the Maps app on your phone and it can locate you in space and figure out what direction you're pointing in? That's done with an inertial measurement unit. It's a gyroscope and accelerometer, figures out your orientation in space. We look at that, measure the values from it, and when you drive your spindle down to touch your workpiece, we can detect the extremely, extremely small amount of movement that generates in origin, and we use that to position your z-axis height. So that drives this down, we get your z-axis height, and now when you say I want to cut 2 millimeters deep or an inch deep, we can compute exactly what that is and drive the motor to that distance. So this board is both the drivers for the motor, so the motor plugs in here, that drives the motor up and down, and then you can see a magnet in here with a clutch. Clutch prevents the z-axis from slipping down under its own weight. And as the z-axis motor spins, magnet spins, and we detect our position. This thing needs to connect to the rest of origin naturally, so that's achieved with a flex cable. Another flex. Richie loves his flexes. And important consideration for this flex, if you look at it closely, you'll actually see it's transparent. This flex is incredibly, incredibly thin. And is designed with a special type of copper deposition process that enables it to be flexible. So because this is moving back and forth with the z-axis, and so this needs to sustain an effectively unlimited number of flexes. And what's so funny is just how matter-of-fact this is. The flex is flexible, believe it or not. Oh shit, that's why it's called a flex.
Whoa, slow down. I need to lie down.
The flexible flex is flexible because of the flexi copper.
Just to really emphasize that point though, take any wire you have that you don't need anymore. If you bend it back and forth, if you flex it a lot, it will eventually break. This has been designed to not break specifically for the application that we need it for, where it is flexing and sliding around.
Now let's talk about the left-right correction motor. We refer to these motors as the user would look at them. So this one would be the left, this one would be the right, as if you're standing in front of the tool. And let's pop the skid plate off the bottom here. So if you could grab me a suction cup.
Suction cup.
If your origin ever gets damaged and you need to send it in to our very excellent repair technicians, they are substantially better at removing these skid plates than I am.
I'm just impressed at how well that's been designed to not just
look at how well that works. So you can see what I did there is I just used the suction cup to remove this. There's a series of plastic clips that hold it in around the side. This is what we would call a double shot plastic piece. So it's a single injection molded part that has a molded in gasket that's captive and part of the component that keeps dust out of the bottom of origin, where all of the exciting correction business is happening.
What's the problem with getting dust in the bottom of origin?
Good question. So in the bottom of origin, we have the mechanism that gets us our left-right correction. You can see the bottom of our spindle collet right here. And so this whole thing moves around, and that's how we move origin to any point in two-dimensional space within this correction circle. So what's the reason for this seemingly crazy looking design? It's a very good question. There's many parts to it. The first is we're designing something that tries to be quite dust-proof. We're designing something that tries to be very compact. So we want this bottom plate to be as small and compact as possible so that you have the maximal working area for your correction range and for the woodworking that you're doing. And we want to maintain a very high holding torque on these motors. So what's actually happening here is the two motors are fixed in space, pointing straight down. You can see the shaft of each motor coming through here and here. And those motor shafts pass through a bearing but are not centered on where that fixing is. So as the motor rotates, that moves in an eccentric motion, so non-circular. And that then moves this arm or this arm, depending on which motor is moving, and that moves the entire correction mechanism so that it's anywhere in the correction circle of origin. And the entire z-axis with the spindle attached to it is mounted to this plate. Yeah, so going back to everything that we've heard now, what is actually happening here is the camera is updating Origin's estimate of its position 100 times per second, and every time it gets an update of its position, it drives the motors to get you perfectly on your design cut line, and it's moving those motors and interpolating them thousands of times per second. So it is moving as fast as possible to always get the motors into position. Okay, yeah, so that's how the base mechanism works.
So we just took a journey from what you as the user see and interface with on Origin through the human-machine interface, the HMI on the display, the spindle, the handles here, to what's happening behind the scenes, how the camera is tracking Origin's position faster than your brain can process it, and how the electronics here drive the motors and the XY mechanism in the base assembly here to, again, keep Origin aligned much faster than a human ever could.
Origin is what I would call an extremely multidisciplinary product development exercise. We talked a lot about the system architecture and what we do to capture images and drive motors. That's a lot on the electrical and the system side of things, but there's a tremendous amount of software that goes into that. Everything from the cloud software that enables you to download designs from online onto the Wi-Fi chip on here, down to the computer vision system, the algorithms that process the domino images, feed them through the CPU, generate position information, down to lower level firmware that runs on our microcontroller in here and drives the motors many, many thousands of times per second to get them into position. All of that is many different layers of software that enable this to happen, and we push updates to that software so that it's constantly getting better. Then there's all of the mechanical considerations for how all this comes together. Every unit undergoes thousands of individual calibrations and tests before it comes to you to make sure it's working exactly the way we think it should be. And everything from the design of this unibody cast tower down to the mechanism that drives the XY motor has been very carefully mechanically designed to make it manufacturable and to last as long as you might be using Origin for. So the engineering team at Shaper is a talented group of roboticists, mechanical engineers, electrical engineers, software engineers, manufacturing engineers, people who care a lot about engineering products, but also a group of woodworkers. We all use the products that we make. We care a lot about making tools for craftspeople. We care a lot about using robotics and engineering to build things that enable people to be creative and to create things. And we're just happy to get to work on such cool things that enable us to take our expertise and knowledge in building robotic and mechatronic systems and to bring that to woodworking.
That's it.
That's it.
That's how it works.
Boom, done. And that's how you make a robot that cuts wood.
Origin to the ground. This is a live scan of the 2.4 gigahertz Wi-Fi and Bluetooth traffic that's flying around this lab. And then over here is our handy dandy oscilloscope, the electrical engineer's best friend. That's how we...
I thought I was your best friend.
Oh,
So
I didn't
sad.
see you had come back in the room, Jeremy.